next question is that, is there any evidence of attosecond charge transport in chemical reactivity, or the influence of attosecond charge transport in the chemical reactivity? I'll give you two examples from literature. One example is based on the Weinkauf work. What they did, they took this a molecule, a big molecule, and then they have selectively ionized this molecule. They know that the selective ionization, they know that the local ionization occurred in this moiety, because this ionization was done through the REMP scheme, resonance enhanced REMPI, resonance enhanced multiproton ionization scheme. What does it mean? It means that this moiety or this chromophore has a particular electronic state, that is the characteristic S1 state. So they have undergone this ladder climbing through this S1 state, and then they have ionized the molecule, which means that they have selectively ionized the molecule at this end of this molecule. So they have removed an electron from here, and when they looked at the fragmentation pattern of this molecule, they have found that this is the fragment which is having 83 AMU mass channel. This is the fragment they have observed. Based on this observation, Weinkauf and co-workers, they concluded that this electron, when you remove an electron, we create a whole charge, whole positive charge, which is nothing but a missing electron. That has to transport to a bond where the bond will be broken. Now, just imagine I have this two, we know that this is the way we can have bonding, and I can have this bonding and anti-bonding orbitals. Okay. Now, if we remove one electron from bonding, so this is your bonding. Let's say this is again hydrogen atom, two hydrogen atom making hydrogen molecule, and this is the MO diagram we can construct very easily. This is bonding, this is anti-bonding. Now, and these are very preliminary chemical problem we have. This is the how we construct the bonding in the hydrogen molecule, dihydrogen molecule. Now, we know that if we remove one electron from bonding, then bond order will decrease, which means I am placing one whole charge here. If I remove an electron from bond from an energy level, or from a MO, a molecular orbital, then we create a whole charge density in it. And if we create a whole charge density, the bond order will decrease and the bond will be weak. And with this argument, Weinkauf and co-workers said that, okay, because we are removing an electron from this end of this molecule, this whole charge has to migrate to this end and sitting probably in this bond, and that's why we are breaking this bond. So this is a very indirect evidence of role of attosecond charge migration in the reactivity of in the chemical reaction. There is another example we have picked up here. In this example, this is an experiment done by Caligari and co-workers. They have ionized this molecule by a pump pulse, and then they have double ionized this molecule, which means this ion has to be doubly again ionized with the help of a probe pulse, this one. And once they have formed this doubly ionized product, they have seen a fragment of this, and they are monitoring this fragment in the mass spectrometer. And when they looked at the fragment mass channel intensity as a function of delay between pump and probe, what they have seen that slowly they have an increase and then there is a decay. There is an increase and then there is a decay in the positive delay. If in the negative delay, they know that the probe cannot ionize the molecule. That's why when probe comes earlier than pump, then you do not produce this ion. we produce this ion only when the pump comes earlier in time as compared to the probe. And that's why they have a build-up signal. This is the transient ionization spectrum. We have already gone over similar kind of transient ionization, spectrum before in this course. Now, when they looked at closely at this regime of this transient ionization spectrum, they have seen an oscillation. This is the oscillation they have observed as a function of time delay. And this oscillation, what does it mean by this oscillation? Let's say I have a process going on. The process is nothing but the production of this ion. We are creating this ion. Now, when we are creating this ion, there must be a probability of creating that ion, and that probability is getting modulated by the pump probe delay time. What does it mean? It means that if some oscillatory behavior of the molecule is affecting the probability of producing this doubly charged cation, then we see that probability goes high, low, high, low. This is the way it happens. So, one can visualize like this way. Let's say in a molecule, what kind of oscillatory behavior I can have? Simplest oscillatory behavior is the vibration. So, in a molecule is vibrating like this way. And when the molecule is vibrating like this way, then in this configuration, I can have higher probability of producing that ion. That's why I have a high yield, then low yield, then high yield, low yield, high yield, low yield, high yield, and that's why we can have this oscillatory behavior of the ion signal. And one can imagine that in a molecule, the simplest oscillatory behavior is going to be vibration, which is nuclear motion, which is oscillatory. So, they looked at the period of the oscillation for the CH stretching vibration. That is the fastest vibration one can imagine for this molecule. We have CH bonds, this is the CH bond. So, they thought that okay, this oscillation could be because of this CH bond vibration. So, what is the period of that CH bond vibration? They found it's going to be 8.9 femtosecond. But then they looked at this oscillatory behavior, and then they found that the period of oscillation, experimentally observed oscillation, is actually 4.3 femtosecond. So, their observed oscillation is much faster than the fastest possible vibration, that is the CH vibration in the molecule. What could be other kind of oscillation in the molecule? There must be some kind of electronic oscillation which is going on in the molecule after ionization. And based on this, Caligari and co-workers concluded that after the ionization, there must be some superposition of electronic states they are creating, and that electronic superposition is changing the electron density and affecting the cross section of this reaction, and that's why they have seen even faster oscillation, faster than the possible fastest vibration in the molecule. So, these two examples are directly pointing out, in fact indirectly pointing out, that there is a role of attosecond charge oscillation and charge migration in the molecular reactivity. Is there any direct evidence of attosecond charge migration we have in the chemical reactivity yet? There is no experiment, to the best of my knowledge, has been performed so far which shows directly experimentally demonstrate that there is an influence of attosecond charge migration in the chemical reactivity. So, with this idea, we started working in inorganic chemistry in the Department of Inorganic and Physical Chemistry, Indian Institute of Science, and we selected a binary complex. A complex, one molecule, two molecules. These two molecules can come closer. They can be weakly bound. Sometimes they are called van der Waals complex. Sometimes they are called non-covalently bonded complex. What kind of interactions they have, we are not interested. But what we are interested is that if we take two dissimilar molecules, let's say one is methanol, another one is water. if we take these two dissimilar molecules and try to ionize one of them, we know that ionization potential will vary depending on the molecule. This molecule may have different ionization potential than this molecule. So, depending on the ionization potential, we can selectively ionize one molecule, and then we can try to monitor whether there is a hole charge which might be delocalized over the entire molecule. So, initially I might create a hole density here, and then slowly that hole density may delocalized over the entire molecule, and that is the goal which we had when we initiated this this attosecond program in Institute of Science. This is an example. Quickly we will be able to understand what does it mean by this electron delocalization, attosecond electron delocalization we are talking about. This is the non-covalently bonded system we selected, and in this cluster, this is a binary mixture. So, we have ClCN, this is one molecule, and ammonia is another molecule, this is another molecule. Two molecules are bound by this dotted line. This dotted line is called halogen bond. Now, they are attractive attraction. This is an attractive interaction. So, these two molecules will not fall apart unless we give the energy. Okay. So, they will be staying close to each other. It's just like a bonding, okay, but it's a very weak bonding, and that's why they stay close to each other. Now, we know that ammonia has lower ionization potential, which means that lower than this molecule, which means that to remove an electron from ammonia, it requires lower energy than ClCN. That's why it is quite obvious that if we ionize this molecular cluster, we will be able to create a hole charge density in the ammonia end. But this hole charge density which we have created is going to be at T equals 0 immediately after ionization. If we create a hole in the electron density, effectively the mean field of the whole electron. So, let us say I have an electronic cloud which is optimized with the help of SCF iteration, that is the self consistent field scheme. So, I have an electron density and I remove one electron from this density. If we remove an electron from this electron density, then we create a hole charge density in the cloud, which means the mean field experienced by other electrons will change, and because it has changed the mean field, we have to re-optimize the mean field. When we are re-optimizing the mean field, we have to remember that we are not changing the nucleus. Nucleus is fixed, nuclei do not change. It is the mean field which will change, and we are trying to optimize it. After optimization in the cationic state of the mean field, we see that there are two orbitals we get, and these two orbitals are nothing but LUMO beta and HOMO beta. So, this is HOMO beta and this is LUMO beta. LUMO stands for lowest unoccupied molecular orbital. I have removed an electron, so that is going to be LUMO, and HOMO beta stands for highest occupied molecular orbital. Now, if we compare, so this is the cationic orbital, optimized cationic orbital, and this is the neutral HOMO, which is representing the initial hole orbital at time t equals 0. What we see from this two diagram is that we can represent this initial state by linearly combining these two orbitals. If we combine these two orbitals linearly, we see that different colors are representing the different phases of the wave function. So, this is your negative, this is your positive, this is your positive, this is your negative, this is your positive, this is your negative. Now, this is positive, this is negative, now this is positive, this is negative, this is negative, this is positive. So, if we linearly add them, what will happen? this negative positive part will cancel out, this negative positive part will cancel out. So, in the end electron density will be localized in this moiety, and that is exactly what we can do mathematically. Mathematically, when we create a superposition state, quantum mechanics suggests that if we create a if the wave function can be time dependent, for any quantum system wave function can be time dependent, but its density may not be time dependent because it is a pure state, and for density it is psi star, and that is why we get time independent density. And remember, all the experimental observables in all the experimental observables in atomic or molecular chemistry, those observables are always connected to the density to the density. So, this density is somehow connected to the experimental observable, not the wave function. We do not see the wave function, we always see the expectation value which is related to the density. So, although wave function can be time dependent for a pure state, in the end density cannot be time dependent. So, experimentally we will not be able to see any time dependence. We see time dependence in density when we create a superposition state, something like this. So, this state, initial state, can be expressed as linear combination of these two cationic states, cationic molecular orbitals, and that is exactly what we are doing. One state is created with the help of this superposition state. So, this is one state which is let us say this is HOMO beta, and this is LUMO beta. So, these two states are combined together. Once we combine together, we get the density, and then density depends on, you see that density will depend on the time. So, time dependent density we will see. So, this is a basic quantum mechanics. We do not see time dependent change in density if it is a pure state. We see time dependent change in density when we create a superposition state, and superposition state we are creating after ionization. The initial whole orbital will be represented with the help of a superposition of the cationic orbitals, and that is why we see the change in density. Now, these are the details of the theory. We can go over the details little bit. What we are doing now is that the initial state of the whole orbital can be represented as a linear combination of all cationic orbitals. So, this is the cationic orbitals, representing the cationic orbital, and the expansion coefficient for this expansion is taken to be the overlap matrix between the cationic orbital and the HOMO, psi HOMO. Psi HOMO is this orbital. So, all we are doing is that we are taking this neutral HOMO orbital and projecting onto all cationic orbitals, all the cationic orbitals, and that is exactly what we are doing. So, if these densities are similar, then we get this expansion coefficient. Densities are different entirely, then this expansion coefficient will go 0, and then we add this time dependent factor, time dependent phase factor, which is coming from the general description of the wave function, time dependent wave function. By this way we are representing the whole orbital. If we represent the whole orbital like this way, then we can reduce down slowly, and finally we can actually get this results. We will go to these results directly. Here what we see that at t equals 0 time, whole density mostly localized in the NH3 moiety, and within 600.6 femtosecond is nothing but 600 attosecond. Within this 600 attosecond, we see that the whole density is delocalized over the entire complex. But again, this is going back to its origin where the whole was created, and this is kind of an oscillatory behavior. So, if as a function of time, if we draw the whole density, how it should look like? It should look like an oscillation. It's just look an oscillation. Total whole density on ammonia is just an oscillation as a function of time. and this will continue forever unless there is an important information we include. We will discuss that information very soon, but what we will do right now is that we will continue and check other non-covalent bonded systems. Previously we have talked about halogen bond where this the definition of halogen bond, we do not need to know the definition immediately, but we can change this X atom, this if it is an X atom, AX interacting with B. Now depending on what kind of X atom I have, if it is an halogen atom then it's called halogen bond, if it is chalcogen atom then it's chalcogen bond, if it is nicogen atom then it's a nicogen bond, it is a tetryl atom then it's called tetryl bond. And this is the way different definition of non-covalent bonds is given in literature. We are not interested in the characteristics of different non-covalent bonding interactions. We are only interested in if they are forming these bonds, and if we selectively ionize or selectively remove an electron from one molecule, how the whole density is delocalizing over the entire molecule. That is exactly what we are interested in. And we see that within almost 500 attosecond time scale, 400 to 500 or 600 attosecond time scale, this whole density is delocalized. So, this is more like an universal response we are seeing for many other systems. If we try to understand what will happen if we selectively, if we hold these two molecules and instead of allowing it to be present in the equilibrium configuration, if we just separate them at a long distance, then again we selectively ionize it. We ionize it from this moiety, we remove an electron from this molecule, and we try to find out at this long distance, do you have the similar kind of charge migration. And we see that beyond at a long distance, let us say 5 angstrom distance, when these two molecules are separated, they do not show any charge migration. This is an important observation because at the equilibrium point, this suggests that at the equilibrium point only or equilibrium configuration only, they are electronically coupled. They are electron and that is why hole can migrate from one moiety to the other moiety. Now I will come to this important point. We said that this whole migration will be oscillatory and it will exist forever. It will just go from one side to the another side partially and then again come back and then again go delocalized, then localized, delocalized, localized. So, this will continue forever unless we introduce one important experimental condition into the problem. The problem is that in this discussion, in this oscillatory behavior, we have considered that the nuclear configuration is R naught, that is the equilibrium point. And any time when you perform an experiment or when you think about a molecule, molecules will always vibrate, and because of its vibration, the 0 point energy state, 0 point state is not going to be the zero vibrational state. It means that even at the 0 Kelvin temperature, when we are at the ground vibrational state, molecule will vibrate. Any molecule cannot be, no molecule can be made vibrationless, but a molecule can be made rotationless because 0 point energy of rotation is 0, but 0 point energy of vibration is not 0, it is some value it has. And at the ground state, it has, if we take the harmonic potential or harmonic approximation, then the ground state wave function, vibrational wave function is represented by a Gaussian function. It suggests that at the equilibrium point, the probability of finding this configuration is maximum, but other configuration will also contribute. And one way to incorporate this idea into the dynamics work is that to use Wigner distribution. With the help of Wigner distribution, one can sample different nuclear configuration and see what is the ensemble average response for this oscillatory dynamics. And for that, what we have to do, we already have shown that we have a superposition state. This superposition state will be multiplied by the ground state vibrational wave function, and then we get the density, because that's exactly what we are interested in. And we see that density will depend on this, finally depend on this time dependent part. And if we do this math, then what we get is that the density, effectively the density will depend on two factors. One factor we have already seen, this cos, that is the oscillatory factor, that's the that causing the oscillation. But this cosine oscillation will be decayed by the by one Gaussian function, and it suggests that this decay is a Gaussian function and this will decay. And what it suggests that because of the vibration, previously we haven't taken vibration, and that's why it will be oscillating always. But because we have now introduced the vibrational effect, the effect of vibration before ionization, what will happen within 10 femtosecond, it suggests that within 10 femtosecond the charge which I am created in a particular end will be delocalized, and it will stop the this oscillation. So nuclear wave packet has a significant effect on the oscillatory behavior of the attosecond charge migration, and this electronic attosecond charge migration is nothing, is driven by pure electronic relaxation due to change in the mean field following ionization. So this is an important idea which we get, and we see that the chemical dynamics of chemical bonding, this chemical, in this problem the chemical bonding is initiated with the help of ionization scheme, and once we ionize it, then new chemical bonding is formed. The new chemical bonding, that is the non-covalent bonding, is formed between these two moieties, and this is exactly what we are probing. And we see that this bonding form, this non-covalent bond is formed with the help of attosecond charge oscillation followed by a few femtosecond damping, and this is very common to all the system we have studied. So far what we have discussed is that attosecond charge migration could be because of the electronic relaxation, pure electronic relaxation. The next slide will talk about it could also be driven by exchange interaction, and exchange interaction is nothing but the behavior of an electron. Electrons are very interesting particles. They have wave particle duality, and also they exhibit exchange interaction. And among exchange interactions, there are two important interactions which is known: ferromagnetic interactions and antiferromagnetic exchange interactions. These interactions are very important in magnetism and also long range electron-electron correlation. Now, the problem which we discussed, this exchange interaction, could be very interesting, fundamentally very interesting problem in the laser ignition chemistry. In the laser ignition chemistry, what we do, we focus a laser beam in the combustion engine. In general, all the cars which we drive at present, they are using spark plug ignition. The spark plug, what does it mean? I have a container. In this container there is a fuel which is injected, fuel, gasoline or petrol. These are vaporized and then injected in the container, and in this container we have a, let's say, spark plug. This is the current technology, spark plug based technology in the internal combustion engine in our car. And in the spark plug, what we do, we have two electrodes, and in these two electrodes we employ very high voltage. When we employ very high voltage, then what will happen, there will be a spark in between these two electrodes, and that spark can actually ignite the fuel, and it can create the self-sustaining combustion, and that's the basic idea of the internal combustion engine. Now, there are many problems of using spark plug in internal combustion engine, and future technology are proposed to be based on the laser ignition chemistry. So, the spark which is created by the spark plug will be replaced by the laser beam, and what happens in the laser beam, we focus the beam at a particular point in the fuel regime where the fuel mixture is injected, and that will create the self sustaining combustion. Now, the spark will be done by the laser ignition at the very high intensity, and the kind of intensity which is proposed to use is more than 10 to the power 11 watt per centimeter square. This is a very highly intense intensity which is required to initiate that combustion. Now, when you talk about this in the fuel injection, fuel oxidizer mixture is used, and in the end fundamentally the whole problem becomes a strong field ionization chemistry of fuel oxidizer mixture. Mostly when we burn fuel in internal combustion engine, we mix fuel with oxygen, and that is why let us say it could be ethylene oxygen mixture, it could be benzene oxygen mixture, methanol oxygen mixture. So, these are the mixtures which is used, and it has been found that when we mix let us say benzene with oxygen, then we see that there are clusters, benzene oxygen clusters which are formed. So, these kind of clusters are formed in the gas phase, and the whole laser ignition chemistry fundamentally can be viewed as strong field ionization chemistry of this kind of oxygen fuel cluster. And when you look at the oxygen fuel cluster, fuel is generally they are singlet, they do not have any unpaired electron, but oxygen, when you think about it, oxygen is a triplet, electronically it is a triplet state. So, when we combine these two systems and try to ionize this system, then we can have two opportunities. One opportunity is that one case we can remove this electron and we can get a quartet state. On the other hand, we can remove this electron, and we can have a doublet state, and we see that this doublet state and the quartet state, they are very close lying. The energy difference between these two spin states are found to be less than 10 Webb number. 10 Webb number could be just an error in the computation. So, they are very close lying, one can say they are very almost degenerate states. What has been found by us that this doublet state only induces attosecond charge migration, but this state do not show any charge migration. Quartet state do not show any charge migration, but doublet state shows charge migration, and that is shown here. This is the charge which we create. In general, fuel molecule shows lower ionization potential than oxygen molecule, and that is why charge is first created in the fuel molecule, which is then delocalized in the whole complex, and that happens only in the doublet state. This does not happen in the quartet state, and that is why we believe that this is due to the exchange interaction, pure exchange interaction in the in this kind of system. This is just the details of similar kind of charge migration dynamics we have observed. So, in the end, what conclusions we make from our theoretical study, we will discuss the experimental study in the next class, but in the theoretical study what conclusions we have made is that ionization of weakly bound clusters actually may enable somebody to capture dynamics of attosecond chemical bonding. Electronic relaxation and exchange interactions both are going to contribute to this attosecond charge migration, and attosecond oscillation followed by few femtosecond damping is quite common in the non-covalent bonded clusters. We will meet again for the experimental part of this work, and we will discuss how high harmonic generation, this is a technique which can be used to probe or get the fingerprint of this kind of attosecond charge migration in non-covalent bonded clusters. We will meet again in the next class.